Example 4.10. A 100-turn closely wound circular coil of radius 10 centimeter carries a current of 3.2 amps. What is the field at the center of the coil and what is the magnetic moment of this coil? First, we'll do the first part. What are the given values? Number of turns, capital N equal to 100. Radius is 10 centimeter, that is 0.1 meter. Current is 3.2 amps. External magnetic field is 2 Tesla. Moment of inertia, that is given here, 0.1 kg meter square. Okay. What is the magnetic field at the center of the coil? Magnetic field at the center of the coil B equal to mu 0 I by 2R multiplied with number of turns. For single turn, mu 0 I by 2R. Here, number of turns is given, so you have to multiply by capital N. Now, we substitute the value. Mu 0 is 4 pi into 10 to the power minus 7 multiplied by number of turns 100 and I is 3.2. Current is 3.2 divided by 2R. If you simplify, you are getting B value as 6.4 pi into 10 to the power minus 4 Tesla. Okay. Now, second part of the question. What is the magnetic moment? Magnetic moment equal to NIA, where N is number of turns, I is current, A is area of the coil. Area of the circular coil, pi r square, pi into r is 0.1 square, that is 0.01 pi. Magnetic moment becomes N is 100 into current 3.2 into area 0.01 pi. If you simplify, you are getting nearly 10 ampere meter square. That is magnetic moment. Now we'll go for the next part. The coil is placed in the vertical plane and is free to rotate about the horizontal axis, which coincides with the diameter. A uniform magnetic field 2 Tesla in the horizontal direction exists such that initially the axis of the coil is in the direction of the field. The coil rotates through an angle of 90 degrees under the influence of the magnetic field. Now, what are the magnitudes of torque on the coil in the initial and final position? Okay, first we'll write the formula. Torque tau equal to mb sin theta. We will try to realize the part now. Initially, this is the coil. Coil is kept in the vertical plane. Therefore, magnetic dipole moment is vertically outward. In other words, magnetic dipole moment and magnetic field both are parallel to each other. The angle theta is between M and B. Angle between M and B equal to 0. So, what is the torque now? Initially, theta equal to 0. Therefore, sine 0 value 0, torque equal to 0. Now, the second part. Second part, we are rotating the coil such that becomes horizontal. Initially, coil was vertical. Now we are rotating by an angle 90 degree. The coil becomes horizontal. This is the diameter, right? Yes. Magnetic dipole moment is always vertical. Coil is becoming horizontal, but there is no change in the direction of magnetic field. Now, if you say magnetic dipole moment and magnetic field, angle between them, theta becomes 90 degree. So, theta value is 90. So, we'll find out torque. Torque equal to mb into sine 90. Sine 90 value is 1. So 3.2 pi into 2, that is 3.2 pi is equal to 10, 10 into 2, 20. So torque equal to 3.4 pi, that nearly it comes to 20 Newton meter. So we got the answer for torque. Now one more part is there. What is the angular velocity acquired by the coil when it has rotated by 90 degree? Moment of inertia is given. We'll go for the last part now. What we have to find out? Angular speed. Okay, we'll start the formula. Tau equal to mb sin theta. In class 11, you have studied tau is also equal to I alpha. We will relate these two. I alpha equal to mb sin theta. What is alpha? Angular acceleration. D omega by dt. So I'll replace alpha by d omega by dt. That is equal to mb sin theta. Now, I'm multiplying both the side by d theta because I want to substitute omega. Omega equal to d theta by dt. So d theta becomes omega into dt. So I d omega dt, d theta is replaced by omega dt, mb sin theta d theta. I omega dt get cancelled. I omega d omega equal to mb sin theta d theta. We'll proceed. Initially omega value 0, then final value, let us take it as omega. Theta varies from 0 to 90. So we'll integrate both the side. Omega value 0 to omega, theta value 0 to 90. I omega d omega, I is constant taken out. Omega d omega integration, omega square by 2. mb sin theta, mb constant taken out. Sin theta integration is minus cos theta. Now we'll apply the limit. I omega square by 2, 0 to omega, no change. So it remains same. I omega square by 2. Now cos theta value 0 to 90. mb is taken out, minus cos 90 minus of minus cos 0. It becomes plus cos 0. Cos 90 value 0. Cos 0 value is 1. So you are getting mb. Therefore, what we got now, left side I omega square by 2 equal to mv. M value is 2. In the previous question, we have calculated magnetic field is 2. And if you simplify, we are getting omega square as 400 or omega equal to 20 radian per second. Now, is there any shortcut for this? Instead of doing all this, shall we go for shortcut method? Yes, that is, see, change in the potential energy. mb cos 0, initial position is cos 0, final position is cos 90. mb cos theta 1 minus cos theta 2, right? Cos theta 1 initially 0, finally 90. So you are getting mb. That is equal to kinetic energy. In rotational motion, what is the kinetic energy formula? Half mv square linear motion, right? You have studied this formula in class 11. Mass is replaced by moment of inertia. V is replaced by angular velocity. So half I omega square is mb. So very simple way we can do this one. Half I omega square equal to mb. We want omega. Omega equal to 2 mv by I under root 2. M value is 10. B value 2, I value 0.1. If you simplify, you are getting 20 radian per second. So this is a shortcut method. You can follow any one of the methods.